As a base balance, we can talk about it now. Before the break, we were looking at pictures like this. We can kind of reabsorb. You can move things across both membranes to affect the blood pH. And then so when I teach acid base balance with the kidney, I kind of use those same figures. And, look at 1, 2, and 3 there. Are you reabsorbing bicarb? Are you excreting protons or hydrogen ions? Are you doing both 1 and 2 at the same time? And that's the key there. Usually to combat acidosis, you want to do 1 and 2 at the same time. You don't always do, but for the most part, if you couple for acid base balance, acid base balance, couple together, reabsorb bicarb. That's your base. Excrete H plus, your hydrogen ions, your protons. That will effectively increase the pH. That will compensate for acidosis. Renal compensation for acidosis. If pH is too high, if pH is too low, you want to raise it. And by doing this, you can do that. Now, the problem is hydrogen ions are too small a molecule to excrete, so you kind of have to lob them onto a bigger molecule. We call those buffers. And so the buffer systems are kind of laid out here. Okay, so the first buffer system we're going to talk about will be, I think it's the amino buffers. And so the thing about bicarb is that I want you to know, it's the most filtered base product. So you want the kidneys to be able to reabsorb most of it. And that's what's shown here. You filter 100% and you reabsorb along the way so that there's very little remaining in your urine. So bicarb is like Tums. It's an acid neutralizer. And so these figures all emphasize the reabsorption of sodium along with the excretion of something. There are different things that can buffer. Again, we have to put this on a larger molecule. This is called the ammonia buffer system. What you do is you metabolize the amino acid glutamine. It's at the top of the figure. You just break that into a bunch of parts. And what they say is they deanimate, oxidate, acidify. So what I'll emphasize is when you deanimate, you break apart that NH3 group. And what you do is you acidify it by like lopping on an H plus. That's how I'll illustrate it. You acidify it, and tag it on there. Now, what you learn that in chemistry is NH4 plus. You know, that's an ammonium ion, right? So NH4 plus is an NH3 that you've acidified, and that's what you excrete in the urine. So you secrete, excrete, and that's what's shown on the left of the figure there. You secrete and then excrete. You trade a sodium with it. I'm not concerned with that. Just focus on excrete, the NH4 plus, reabsorb, a new bicarb. Reabsorb bicarb. New. And the word new is very important. It actually has meaning. Why is it new? It's because you've coupled it with the excretion of a hydrogen ion. So you have one less hydrogen ion and one more bicarb. That makes it new. And that'll help you effectively raise the pH when pH is too low. Okay? So that's the effect of ammonia buffers. Remember glutamine. Students tend to forget that. That's how it all starts. Cells can metabolize that and you excrete the ammonia buffers there. You have other buffers, like for example phosphate. Phosphate is monophosphate, okay? Monohydrogen phosphate. So what I said was monohydrogen phosphate buffers. Oh, something I didn't mention is pay attention to where you are in the nephron. That says collecting duct. We haven't gotten there yet, but we can talk about it now. We have these cells in the collecting duct. These cells were in the PCT. We just talked about that before. So this happens in PCT. This happens in collecting duct. Okay. What I'm focusing on is what you excrete or reabsorb. So monohydrogen phosphate, well, it's right there. It's in the filtrate there. Let me write it down. That's the molecular formula there. And what the PCT, or excuse me, what the collecting duct cell is doing, it's using carbonic anhydrase to hydrate the CO2 to make carbonic acid. Okay. I'll just draw it like they do there. H2O plus CO2. It gives you the carbonic acid. That's a weak acid that will partially dissociate to your hydrogen ion, H plus, in your bicarb. So what the figure is showing you is that you acidify in the filtrate the monohydrogen phosphate to dihydrogen phosphate. So that becomes H2PO4. Okay, that is what you excrete. So you excrete in the urine. Again, you reabsorb the bicarb, and that bicarb is new because you coupled it by excreting with the phosphate buffer. Okay, so that's the same thing, right? It's the same thing. You couple those things together. You do it differently. All right, before you metabolize glutamine, here you're utilizing carbonic acid, breaking it into its parts. And, so let's just talk about that. Let's talk about the bicarb buffer system. And so this figure is really confusing. I don't even know why they make things like this. Like, where do you look? I guess you can follow the steps. It's still confusing as heck. And I've studied it, and I actually like to start at number 6. I actually like to start there. So this system has to do with the bicarbonate buffers. Number for bicarbonate is HCO3, full negative charge. And number 6, it starts with CO2 diffusing into the cell. Okay. Now, again, they hydrate the CO2 with water. It's the same equation, just drawn a different way with carbonic anhydrase. And that partially dissociates into your hydrogen ion plus bicarb. It's the bicarb that's reabsorbed. Now, I have a question for you. Look at the figure, which I said is confusing, but where does the hydrogen go? Let me see. I said start here, boom, keep track of your hydrogens. I see H2O, I see H2 there, then what? There's an H, there's an H, one H is in the bicarb. Where's the other H? It goes there, then what? H2CO3, then what? It's in the form of water. Now here's the thing. You reabsorb most of the water, so you're not really getting rid of the proton in this example. Okay. Think of water as a hidden proton. Good old H2O. It's actually H plus OH. It's a hidden proton. You reabsorb most of water. So I'll put reabsorb. So you're not excreting the proton this time. So you do recover the bicarb, but I'm not going to call it new. Do they call it new? No. You just put it there. So you're replenishing your bicarb. And also, that bicarb reabsorption, it's not direct. It's an indirect reabsorption. Let me write that on the board because it's on the next slide, that idea. So when you reabsorb this bicarb, an indirect reabsorption. That's kind of what we say about this mechanism. What did I say entered the cell? CO2, not bicarb. Here's the bicarb that's been filtered. This bicarb is not the one that ends up there. It's the bicarb that happens as a result of the CO2 entering and then going through that chemistry. And this bicarb is the bicarb that's, well, indirectly reabsorbed. That's kind of what we say. So here are two questions I always kind of pose to students for this part of the lecture. Bicarbonate is indirectly reabsorbed. What is meant by this? That thing I just said, right? It's not bicarb that actually enters the cell. It's CO2. And then you indirectly reabsorb bicarb. And the amino acid glutamine, I said, how does it increase pH? What was the name of this buffer system? Ammonia. So think about the NH3 group that becomes NH4+. That's what I'm going for there. Students tend to forget about glutamine in this part of the lecture. All right, so that's how kidneys can help combat the acidosis. They can combat alkalosis too. I'll get into that later. So any questions on acid-base balance? I did ammonia, phosphate, and bicarb buffers, those three. Okay. Well, anyways, I kind of want to get back to the theme of going through the nephron. I did glomerulus, I did PCT. After the PCT comes the leukopenny, which is a hairpin loop. And what the kidney can do, it can help regulate blood osmolarity at 300. So let me write that number on the board. Books tend to use that number a lot in renal lectures. think of that as biological saltiness. Osmolarity. Remember, osmolarity is just osmosis, the saltiness of something. It makes water diffuse, right? Water goes to where it's like there's more stuff, it's more salty to dilute things out. Well, anyways, blood osmolarity is something like 300. So that's a really dilute solution. It's like saline. Saline is 0.9% sodium chloride. So that's like that. So imagine a beaker with 100 ml water, and you add 0.9 grams of salt. That's not very much, right? That's what that number is. Well, anyways, that dilute fluid, what you're going to do in the loop, you're going to pull water out, okay? And there's a countercurrent mechanism to pull water out as well as salt. This dramatically varies urine concentration, and so you can kind of maintain blood plasma at about 300 by doing that. So here's a picture of what we're going to talk about. Now, we have two kinds of nephrons. The ones that help concentrate urine are these ones, because the loop of Henle's extend deep into that salt gradient, which is the medullary pyramid. All right. So here's a picture of it there. Well, what they're showing you here is the salt gradient. The medullary interstitium. Maybe it's 300 close to the border of cortex and medulla, but maybe it multiplies to 1200 at the bottom. It gets progressively saltier by about 4 times. Now, what creates, it starts out all 300, but the loop of Henle, it kind of creates this salt gradient and maintains it. So that's kind of what I want to teach. And so you extend these loops and you put the filtrate through it, and it has an ability to create and maintain the salt gradient. It acts as a countercurrent multiplier. Loop of Henle acts as a countercurrent multiplier. What do you multiply? Well, in the end, you're going to have multiplied the medullary fluids or interstitium to be 300 to 600, or 300 to 600, 900 to 1200. That's 4 times the amount there. The other thing we like to talk about is the blood supply to those long loops of Henle. That's the vasa recta. So what you got to do is you got to supply blood to this area without messing up the salt gradient, because if blood is always flowing through, you can wash away the salt gradient. So you have to have a mechanism to have exchanges of materials, including the blood gases, but preserve the salt gradient. So we're going to see that the vasa recta is a countercurrent exchanger, and it preserves the gradient. And the term countercurrent simply means when you have a hairpin loop, that fluid is flowing in opposite directions. That's what countercurrent means. And we're going to see why this is a countercurrent multiplier and exchanger. So what they got here, let's see here. So you have this loop. They kind of draw like this thick segment that descends, and then it kind of thins out. And then it kind of goes like through a hairpin loop and turns back around. Then it kind of gets thick again. Kind of goes back up. So this descending segment is thick and thin. I care more about this one. This thin descending limb of the loop of Henle. What you see there is it's kind of leaky. It loses fluids. And I think that's why it kind of thins out. If you're a tube and fluid is leaving, you're gonna kind of get smaller over time. Right? So this is water permeable, is what we say. The filtrate loses water, and that kind of concentrates the filtrate. filtrate, loses water, concentrates, filtrate. It's losing water because it's coming in 300, right, dilute. And it's going through this salt gradient, which is becoming progressively saltier. And because, well, rules of osmosis, and it's water permeable, on the way down, water is leaving, correct? What we're seeing there. So when you get to the elbow, they kind of make the fluid more brown at the elbow, right? They're trying to illustrate to you that the filtrate inside is very concentrated. The filtrate at the elbow is 1200. It's going to match the environment it's in. So I'm just going to draw 1200 to point to like 1200 is the concentration around this area, but also inside the tube, because you just passively lost water by rules of osmosis on the way down. So you've pulled water out. Okay, now on the way up, it's kind of different. You do this counter-current thing. So on the way up and out, things happen. And what I want to illustrate is the thick ascending limb is watertight. They try to illustrate that to you. They put these dark brown lines there to illustrate that it's watertight. Just kind of put some dark brown there too. So there's a thin part and a thick part. I'll focus mostly on this thick ascending limb. Not the thin part, the thick part. Sometimes books abbreviate that TAL. The TAL, those have salt pumps. Okay, and they're watertight. So I'll put those two features. Cells contain salt pumps, but the cells are watertight. I'll say watertight. Impermeable to water. Water ain't gonna leak out. Yeah, that's what I'm trying to say. Watertight. So you're gonna pump out salt and not lose fluids. So that's gonna re-dilute you. And you're gonna get the sodium that you're trying to conserve. So on the way up, don't lose water. Pump out salt. Okay. So the end result of this is, for the thick ascending limb, I guess you re-dilute filtrate. So they gave you two things to understand there, and it's not too difficult. I think I can follow it. Lose water on the way down, and what do you lose on the way up? Salt. Now what this does, this counter-current thing, it creates this positive feedback loop that makes sense of why you get this multiplication of 300 to 1200. So here's the loop. And I'm going to do what I usually do. When they say start, I'm actually going to start somewhere else. I always think differently than a doctor. But it doesn't matter because it's a loop, because I'm going to end up there, right? So it doesn't matter where I start. So this right here creates a positive feedback loop, but I'm going to erase my picture now. I'm going to start where I started, where the fluid's coming in. The thin descending limb. That's the first thing that comes in, and what happens? You lose water. leaves. Boom. That's the first concept for the thin descending limb. So as you go down, when you get to the elbow, what happens? You increase the saltiness. Okay. As you go down. Increase OSM of filtrate. That's the next concept, circle that. And I'll even add one. At the elbow, that little turn, what did I say the concentration of the filtrate was? Give me a number. 1,200. Right there. 1,200 millosmolar. Okay, circle that. Okay, now you're going to start to go out. Go up and out. Okay. Well, that means that you have increased saltiness of the filtrate entering the ascending limb. Have increased saltiness, osmolarity, of filtrate entering, I'll just say TAL, right? That's how I abbreviated it. So what that means, what they're trying to tell you is, okay, so you have, because you've concentrated it, it makes it easier work for the cells of the TAL to pump it out. So salt's pumped out. By TAL cells. Right? What was the next point? Well, what that does at the top of their loop is, well, you've increased the interstitial saltiness, the interstitial osmolarity. Running out of room here. Let's see here. Here's this title. Increased saltiness of medulla. That's what I'll say. Let's connect that concept to that one. So because you've increased the saltiness of the medulla, that influences this. More water will leave. Because more water leaves, you got more saltiness of the filtrate at the elbow, and you got more salty. And this keeps going around and around and around. It's not going to stop. It'll just keep going. Because you lose water on the way down. This water that you lose, it doesn't wash away the salt gradient. Because you got that hairpin loop, you turn back up, you keep pumping it out on the way up, you keep that multiplication factor going. So it's 300 to 1,200 at the bottom. Okay. Are there any questions on why this is a feedback loop? You just keep going around and around. And that's why it remains that way. Maybe when the kidneys first develop, it's 300 from top to bottom. But when this starts going, eventually you get it to 300 to 1,200, and it stays that way. So the thing about it is, we've got to talk about the blood supply to this area, which is the vasa recta. And so we show it as a separate slide, but imagine the loop of Henle, which is a loop, with a loop-shaped capillary bed, the vasa recta. Okay? Just kind of look at that. So the loop of Henle was a countercurrent multiplier. We say this is a countercurrent exchanger. It's not multiplying anything, it's just making passive exchanges. Countercurrent exchanger. The goal is to just protect the gradient. Don't change it. That's what I say at the top there. Preserve, protect gradient. Preserve / protect this salt gradient. You want to have the blood flow through there, but you don't want to wash away the salt gradient. So you do so by making passive exchanges. So look on the way down. On the way down, let me point to it right there. Blood coming from the efferent arteriole, right? It's coming in 300. And it's entering an environment that's becoming more salty, 300 to 1200. So as you go to where it's more salty, does it make sense that they're saying salt enters, water leaves? As you enter, the water in the blood is going to leave because it's getting more salty as you go down. That makes sense to me. But because you're losing water, the blood is getting more concentrated. Okay? So, I don't know, 400. It's getting more salty because it's getting more salty. Now, salt's going to enter. You're just making passive exchanges. I'll draw it a couple of times. You're just equilibrating with the environment. That's how I think of it. You're just making passive exchanges, equilibrating with the environment. Water leaves, salt enters. So at the elbow of the vasa recta, you just equilibrate at 1200. Now, why did it change from red to blue? Gas exchange. Gas exchange does occur here. It doesn't occur at the glomerulus, as we've been saying. So you just make passive exchanges. But now here's the kicker. It's not a normal capillary bed. It doesn't just go straight out. It actually takes a U-turn and goes back up, right? So now you can make passive exchanges on the way up as it gets progressively less salty, I guess. So the blood is really salty, and as this blood enters, it's becoming more dilute in its environment. So it's going to lose salt, gain water. Lose salt. Lose salt. Gain water. Gain water. So as you get out of there, it should be almost as salty leaving as it is entering in. In this book, it says it leaves around 325. It's not bad. Okay, it's a little more salty. The point is, you didn't really remove very much salt. Okay, by going all the way down and equilibrating, and going all the way up and more or less equilibrating, you're preserving that salt gradient, and you made all the exchanges you needed to. You supplied nutrients, you had gas exchange, and you preserved the salt gradient. Because the big thing about this is you want to pull all that water and salt out so you don't dehydrate yourself. Okay, so that's the net effect. You preserve, protect the salt gradient at the vasa recta. The next part, I think I want to pick it up here next time. I still want to give you guys some lab time to start studying urinary. And so for the remainder of class, just remember, when's your lab practical? It's on a Monday. It's December 9th, I believe. And so just keep track of all the time I'm giving you. On Wednesday, it's not a holiday, so I'll be here. It is the Wednesday before Thanksgiving. That's the one day I'll say, well, you know, if you didn't make it to class, it's not going to count against you. You can just watch the lecture on YouTube.